Imagine yourself adrift in the vast expanse of space. The darkness of the cosmos gently envelops the twinkling stars, which shimmer like distant flames, murmuring ancient secrets. Our universe, this grand and dazzling realm, serves as the abode for immense celestial bodies. These entities captivate the human spirit with their mystery and irresistible power. Consider a star, an enormous sphere of gas, burning fiercely, illuminating the cosmic night through thermonuclear reactions deep within its core. There, hydrogen atoms collide and fuse with helium atoms, akin to an eternal symphony of life and death, unleashing radiant energy. The universe harbors trillions upon trillions of such stars, and our sun is merely a minuscule grain of sand in this infinite desert. It bathes our blue planet in familiar flames with each dawn. Yet, concealed within that obscurity lurks the most terrifying presence, the black hole, where everything concludes in absolute silence. Matter approaching it is mercilessly devoured, torn, and stretched by an inexorable gravitational force. It echoes like a whisper of death emanating from the fabric of space itself. Beside it, the universe cradles majestic spiral galaxies, with nebulous clouds unfurling like abstract paintings by the Creator. Orbiting planets and streaking comets, numbering in the billions, each bear unique tales of formation and transformation. So, whence originate these countless celestial bodies in the universe? Were they born amidst chaotic moments, or through patient, gradual processes? The answer resides within the universe itself, in a narrative commencing from the very first instant of existence. Let us journey back to the year 1927. The Belgian astronomer Georges Lemaitre, a brilliant priest and scientist, drawing upon Albert Einstein's general theory of relativity and early astronomical observations, boldly proposed that the entire universe expanded and evolved from a primeval atom. In essence, the universe originated from a Big Bang, with space and time erupting from nothingness, spreading like a sound wave reverberating through space, bringing forth the cosmos's initial breath. In that primordial phase, the surroundings consisted primarily of a foggy gaseous cloud composed of light elements, hydrogen and helium. Like morning mist over an infinite ocean, these clouds drifted slowly. No luminous stars yet existed, only cold silence governed this nascent, unawakened universe. However, at that juncture, gravity, one of the four fundamental forces of the universe, described by Einstein as the curvature of spacetime, began to exert its influence. Like an invisible hand, it drew together regions of higher density in the gaseous clouds. Under gravity's might, these clouds coalesced and accumulated, with internal temperatures and pressures rising explosively, akin to a boiling cauldron. Ultimately, they ignited themselves, giving birth to the first generation of stars. These were the initial flames piercing the darkness, heralding the glorious era when light conquered obscurity. With the emergence of innumerable stars, they began clustering with dark matter, a mysterious form comprising approximately 27% of the universe, invisible yet providing the gravitational scaffolding necessary for structure, to form vast celestial systems known as galaxies. Swirling like cosmic vortices, cradling billions of stars in an eternal dance. Naturally, our own galaxy, the Milky Way, was born amid that turmoil, a luminous whirl through which we hurtle at astonishing speeds. Scientists estimate the Sun's age at approximately 4.6 billion years, confirmed through radiometric dating of lunar rocks and meteorites. Around 4.6 billion years ago, the Sun formed like a fetus within a gaseous cloud in the Milky Way. In its infancy, it was encircled by thousands of rocky fragments, remnants from the deaths of previous generations of stars, scattered by supernova explosions that dispersed heavy elements far and wide. These remnants laid the foundation for life. Thanks to gravity, they collided and merged repeatedly, piecing together like puzzle fragments to form the planets orbiting the Sun. Mercury with its scorched surface, Venus shrouded in thick atmosphere, our blue home Earth, and all the planets, spheres of rock and gas, dance in the cosmic waltz. Gravity sculpted the universe's celestial bodies, crafting habitats for all life. This is a wondrous process that evokes profound awe. Observations from the Kepler Space Telescope, launched in 2009, have revealed thousands of exoplanets, demonstrating that most stars in the Milky Way possess their own planetary companions, like friends on a solitary journey. Moreover, the James Webb Space Telescope, launched in 2021, has unveiled hundreds of potential planets, including rocky worlds that may harbor liquid water, igniting hopes for life beyond Earth. Those deep infrared images captivate the soul with their enigmatic beauty. Recent discoveries by the James Webb Space Telescope in 2025 include observations of a supernova exploding when the universe was merely 730 million years old, exoplanets with atmospheres defying existing models, and detailed hierarchical views of colliding spiral galaxies. Additionally, there are ancient supermassive black holes dubbed little red dots, rogue black holes, and black holes at galactic centers, capturing accelerated growth processes. These findings bolster hypotheses of rapid black hole growth in a relatively small universe and reinforce the direct collapse black hole theory. To further kindle curiosity, let us incorporate some of the latest revelations. In 2025, the James Webb Space Telescope confirmed an actively growing supermassive black hole in a galaxy just 570 million years after the Big Bang, challenging our comprehension of black hole formation in the early universe. Furthermore, it observed the third known interstellar object, now designated as Comet 3I Atlas, a visitor from another stellar system bearing information about distant cosmic regions. These discoveries, like riddles, invite us to probe the universe's origins, fueling boundless curiosity about the unknown. On a broader cosmic scale, let us expand our perspective. The number of stars may exceed the total grains of sand on Earth, approximately 70 sextillion stars compared to 7.5 sextillion grains, rendering us feel minuscule, like a droplet in the ocean. They are dispersed across the observable universe, with a diameter of 93 billion light-years, a distance that light, the swiftest entity in the cosmos, would require 93 billion years to traverse. Our abode is but a tiny corner, yet illuminated by the brightest stars, reminding us of the miracle of existence. To add depth, let us contemplate recent theories. In 2025, certain breakthroughs in physics include the discovery of an object equivalent to 50 million solar masses, confounding theories of the young universe. Moreover, novel theories suggest the universe's origin may not necessitate inflation but could arise through alternative mechanisms, upending conventional views. Additional insights from 2025 indicate that dark energy might be weakening, potentially leading to a big crunch where the cosmos contracts due to evolving dark energy, as proposed by South Korean researchers. The universe may also be lopsided, challenging the standard cosmological model, and new maps from tracers like galaxies and quasars offer the most comprehensive view yet. These enigmas, like concealed treasures, prompt contemplation of the universe's five great mysteries. Why does matter prevail over antimatter? What constitutes dark energy? How does gravity unify with other forces? These questions blend academic rigor with a pursuit of the mysterious in modern science. Nevertheless, the universe is not eternal. All celestial bodies possess finite lifespans, a melancholic truth that arouses curiosity about their demise. Massive stars, upon exhausting their nuclear fuel, cannot withstand their own gravity and ultimately collapse into black holes, like perforations in spacetime that engulf everything. Smaller stars will fade slowly in the distant future, transforming the universe into a frigid expanse nearing absolute zero. This scenario, termed heat death, has been profoundly pondered by physicists such as Stephen Hawking. One day, the universe shall revert to eternal darkness, but until then, reflect upon the secrets preserved by black holes. These entities evoke both fear and fascination. Gazing back from a black hole's edge, you would behold hundreds of versions of yourself, repeating like phantoms in infinite mirrors. This is no sorcery, but the photon sphere, a shell where light is trapped in circular orbits, bent under extreme gravity, like an immortal ring of light. Merely 15 seconds later, light could not even escape from your eyes, vanishing into obscurity. Today, let us explore a harsh yet captivating theme: what transpires if you are cast into a black hole? This is not science fiction, but grounded in actual physical reasoning, from Albert Einstein's general theory of relativity to contemporary models. Before casting you in, let us revisit what a black hole entails. Einstein even regarded black holes as places where God divides by zero, absurd points of infinite density. He disbelieved in the actual existence of these monstrosities in our universe and published a paper in 1939 arguing that stars could not collapse into singularities. However, humanity has detected them through stellar orbital observations, gravitational waves from the Laser Interferometer Gravitational Wave Observatory in 2015, and the first image of the M87 black hole by the Event Horizon Telescope in 2019, followed by the Sagittarius A image in 2022. Particularly, immense and dense stars undergo horrific transformations at life's end, collapsing upon themselves. Nothing remains but a mysterious point in spacetime called the singularity, possessing infinite density and infinite gravity, where physical laws crumble. Recent discoveries in 2025 include 3 supermassive black holes in a collision process, a cluster of supermassive black holes from 10.8 billion years ago, and observations of ultraviolet and X-ray light associations varying over billions of years. This implies that black holes' fundamental nature is evolving and reignites theories that our universe may reside within a black hole of another universe. To expand this mystery, let us add more. In 2025, scientists identified the fastest-growing black hole ever using the Chandra X-ray Observatory, along with an explanation for an impossible merger of 2 colossal black holes. This resembles a hidden cosmic script, revealing how black holes formed rapidly in the early universe, challenging extant models and stimulating discussions of mirror worlds or alternative gravity theories such as modified Newtonian dynamics. The general theory of relativity introduced a revolutionary concept: gravity is not a force acting upon objects but the curvature of spacetime induced by mass. Like a heavy ball stretching fabric. This elegantly explains Earth's orbit around the Sun and the harmonious cosmic tableau of other planets. Inside a black hole, there is no black material surface. The singularity is merely density so extreme that it warps spacetime into a profound well, with walls so vertical that nothing can escape. Ironically, in the same year of 1939, J. Robert Oppenheimer, renowned as the father of the atomic bomb, and Hartland Snyder published research indicating that stars could collapse under their own gravity into black holes. This was a pivotal point that compelled Einstein to reconsider, though he never conceded. Now, let us narrate what would occur if you were cast into a black hole, a skin-chilling yet profoundly curiosity-igniting notion. Astonishingly, any entity could become a black hole, a star, a planet, even a diminutive being like ourselves, provided it is compressed to the Schwarzschild radius. The German physicist Karl Schwarzschild, in 1916, first discovered an exact solution to Einstein's field equations, a simple yet elegant finding, with the radius calculated by the formula 2gm(c²), where g denotes the gravitational constant, m the mass, and c the speed of light. For our Sun, compressing its entire mass into a sphere of 3 km radius would render it a black hole. Earth would be approximately 9 mm, the size of a marble. A human becoming a black hole would necessitate compression smaller than a proton, though inconceivable, yet if so, you would become an entity devouring all around it. Into which black hole shall we cast you? Small ones lack intrigue. Stellar black holes of several solar masses would rend you into spaghetti-like strands via tidal forces before reaching the event horizon. Let us select a large one, with an event horizon exceeding our solar system's span, supermassive black holes of billions of solar masses, where tidal forces are gentler, permitting longer survival to witness wonders. But not excessively so. Let us choose a nearby one, Sagittarius A, the supermassive black hole at our Milky Way center, approximately 4.3 million solar masses. You orbit it already at 220 kilometers per second. It is one of 2 black holes humanity has imaged, revealed by the Event Horizon Telescope network in 2022 as a dark shadow encircled by a luminous ring. Recent observations in 2025 include infalling gas winds, artificial intelligence analyses indicating it spins near maximum velocity, and stellar orbits more stable than previously deemed disruptive. Furthermore, rapid light displays confirm the galactic center as an ideal laboratory for black hole studies. These details, like enigmatic invitations, deepen our exploration of cosmic centers' mysteries. Now, set the scene, a heart-pounding tale. You and I voyage thither, docking our spacecraft at a safe distance of 1 trillion meters from the event horizon. The air remains calm, yet you sense a faint gravitational tug like a breeze. I permit you to free fall towards the black hole, observing with a blend of concern and exhilaration. Crucially, according to general relativity, time near a black hole diverges markedly for the one nearby versus the distant observer. Time dilation occurs, time slows near gravitational sources. As vividly depicted in the film Interstellar, an hour on a planet near a black hole equates to 7 years on Earth. I equip you with a special clock recording time from your perspective and mine on the spacecraft, synchronized. You venture towards the maternal universe's heart, commencing a journey into darkness. Upon falling, you behold the spectacular sight of the distant black hole devouring matter. The accretion disk, a vortex of gas and dust, heats to extreme temperatures via friction, glowing like infernal flames. Simulating this scene on a notebook typically requires over a decade, but in reality, the disk may emit blue or white light, though appearing orange for observational ease. At the first clock check, 30 minutes have elapsed, and you have traversed merely 0.1% to the event horizon. My spacecraft leads you by 11 seconds, but the disparity is not yet alarming. Silence envelops you, the universe whispering farewell. Now closer. Space-time around the black hole creates bizarre visual effects. Light from the sides, even behind, bends into your eyes, like a distorted lens. Checking the clock again, you have fallen for 2 hours, completing 1.4%. I lead by 44 seconds. The disparity begins to unsettle, though not yet frenzied. A profound sense of isolation assails you, as the universe severs you from the familiar world. The black hole's central darkness expands faster than anticipated due to gravitational lensing. Light curving through strikes your retina, crafting illusions that confound the mind. After longer durations, the clock shocks. From your perspective, 12 hours have passed, but my spacecraft perceives you absent for nearly 15.5 hours. Now exceedingly near, everything turns extraordinarily peculiar, like a nightmarish dream. Before the irreversible point, you pass through a wondrous locale. At this special point, time halts, and surveying surroundings would astonish you. Your heart pounds, captivated by mystery. You arrive at the photon sphere, one of the universe's strangest places, where gravity perfectly balances, permitting photons of light to orbit the black hole in circular paths. It is not luminous matter or reflected light, but trapped light particles, like wandering souls unable to escape. If light moves tangentially, it circles eternally. Deviate slightly, and photons either plunge into the black hole or flee to the cosmos. Under these conditions, gazing about from the photon sphere, you would see innumerable reflections of your own nape. Like standing beside yourself in real time, sans special effects, all due to spacetime curvature. A phenomenon profoundly explored by Roger Penrose in singularity theory, for which he received the Nobel Prize in 2020. Continuing the journey. The event horizon looms very near. Beyond the photon sphere, the black hole increasingly dominates the view, evoking a sensation of being engulfed by darkness. Primal fear surges. The obscurity warps surrounding space, revealing the black hole's rear and edges, parts invisible in flat space, like an infinite curved mirror. You have fallen 13 hours, with 24 minutes remaining to the event horizon. Yet my spacecraft has observed your journey for nearly 20 hours. Time stretches like eternity. Another 18 minutes pass, checking the clock, I have observed almost 40 hours. Your final 18 minutes equate to 18 hours for me. The disparity makes you realize time is an illusion. The last moments, 6 minutes until crossing the event horizon. You close your eyes, draw a deep breath, glance at the clock. It appears malfunctioning, displaying my observed time as infinite. But it is no fault. It is a physical marvel. From the spacecraft, I see you slow asymptotically towards the horizon over decades. Eventually, you fade and redden due to gravitational redshift, visible only to infrared telescopes. Even if immortal, I would never witness you actually cross the horizon. For you, it is the final 6 minutes, for me, eternity. This sounds like science fiction, yet derives directly from Einstein's equations. Now you are within the event horizon. What occurs inside? Strangely, you might scarcely notice crossing the boundary. You can still view the external universe, distant stars twinkling, my spacecraft a solitary point of light. But all that light, like you, hurtles towards the singularity. At that point of infinite density, physical laws collapse, and time ceases. Escaping the singularity's gravity demands exceeding light speed, impossible per relativity. A common misconception, gazing back at the external universe, due to extreme time dilation, you could witness the entire future history of the cosmos accelerate. But this is entirely erroneous. As you rush inward, the external universe compresses into a thin band, like a flattened picture. Ultimately, sufficiently near the singularity, the process of bodily elongation, spaghettification, commences, where tidal forces stretch you into long, thin strands, as detailed by Kip Thorne in Wormhole Research. You merge with the black hole, adrift eternally in the cosmos. The mere contemplation chills the spine, yet profoundly ignites curiosity, prompting questions of whether the universe conceals greater secrets. Black holes, those enigmatic celestial bodies, evoke both love and fear. Stephen Hawking's theory of Hawking radiation, where black holes evaporate over time via quantum effects, or Roger Penrose's singularities. Even ideas from scientists like Nikodem Poplavsky that our universe resides within a black hole of another, connected via wormholes, opening new vistas. Reliable social media from the National Aeronautics and Space Administration or physicists' accounts on X in 2025 discuss inclusions such as black holes potentially lacking singularities and instead transitioning to white holes that eject matter. James Webb Space Telescope findings of an earlier-than-expected universe prompting reconsideration of dark matter, which provides the gravitational framework for galaxy formation, or the rise of alternative gravity theories like modified Newtonian dynamics. Moreover, new theories such as cosmic knots may explain the universe's existence, alongside ideas of mirror worlds for dark matter's origins. These modern insights, like invitation letters, fuse academic zeal with a pursuit of the mysterious. At the intersection of science and mystery, we continually question our place in this grand panorama. Finally, express profound gratitude to the scientists and researchers mentioned in this article, and their collective endeavors. Georges Lemaitre's bold Big Bang proposal, Albert Einstein's genius insights in general relativity, Stephen Hawking's profound reflections on Hawking radiation and heat-death scenarios, J. Robert Oppenheimer and Hartland Snyder's predictions of black hole collapse, Carl Schwarzschild's discovery of the Schwarzschild radius, Roger Penrose's singularity theory, Kip Thorne's explorations of spaghettification and wormholes, Nikodem Poplavsky's notion of universes within black holes, all represent dedications to human knowledge. Furthermore, acknowledge the persistent and devoted efforts of the Event Horizon Telescope team, Laser Interferometer Gravitational Wave Observatory researchers, James Webb Space Telescope team, scientists from the National Aeronautics and Space Administration and European Space Agency. Their quiet dedication illuminates cosmic secrets, inspires society, and guides us all towards enhanced understanding. Extend sincere thanks for their contributions. To expand this gratitude, let us recognize some collective achievements from 2025, such as early universe supernovae and black hole clusters discovered via the James Webb Space Telescope. These international collaborations advance our comprehension of cosmic origins, stimulate global curiosity, and remind us how science transcends boundaries to unveil mysteries.